All right. Good morning, everyone. Okay, so we'll go and get started. All right, so today we'll be talking about alcohols, ethers, and thiols. Okay, can everyone hear me on Zoom?
Yeah.
Okay, thanks. All right, this is the alcohol functional group. It has the pattern COH. The oxygen is tetrahedral. Okay, it has 4 electron groups, and that results in a bent molecular geometry around the oxygen atom. Okay, we had just gotten started on this last time. We'll take a look at names of alcohols. Okay, you can recognize the name of an alcohol because it will end in OL. Okay, we drop the E and then we add the suffix OL. Common names will be followed by the word alcohol. All right, so these are some examples of both IUPAC and common names. Okay, there's a lot of use of common names commercially in the United States still. Many chemical suppliers are listing both the IUPAC and the common. Okay, here is ethanol, okay, from ethane. Okay, it doesn't matter where we put the alcohol group, it's still the same. With propane, it does matter. You have 1-propanol or 2-propanol, also called propyl alcohol or isopropyl alcohol. Okay, 1-butanol. Okay, we do have to locate the alcohol. This is called butyl alcohol, or it may be just called N-butyl alcohol. 2-butanol. Okay, this is a sec-butyl group. It's a straight chain. The alcohol is on the second carbon. 2-butanol is the IUPAC, sec-butyl alcohol is the common. Okay, here's isobutyl. Okay, both 1-butanol and 2-methyl-1-propanol are primary alcohols. Okay, whereas secondary, sec-butyl is the secondary. Okay, here's tert-butyl alcohol. 2-methyl-2-propanol. Cyclohexanol on a ring such as cyclohexane, we don't have to specify a location. It's assumed that the alcohol is on number 1. Okay, and I think this is as far as we got last time. All right, so here we have 8 carbons. The alcohol is on carbon number 1. Okay, so this would be 1-octanol. Drop the E, 1-octanol. Okay, you might also see it, this is actually the newer method, and that's to name it as octan-1-ol. Okay, where we have the location number closer to the suffix. This is the older, this is the newer. All right, longest chain is pentane. This is part B. Right, if we go this way, the methyl's on 2. If we go this way, the alcohol is on 2. The alcohol takes priority. Right, so, okay, so this would be 4-methyl 2-pentanol, pentane for 5. 4-methyl 2-pentanol. Right, letter C. Okay, again, it's assumed that the alcohol is on 1. The alcohol takes priority. So this is cyclohexanol. It's not correct. It's not incorrect if you call it 1-cyclohexanol, but the 1 is not necessary. And this is 2-methyl. And the geometry is trans. Trans 2-methyl cyclohexanol. Okay, and then the last one. Okay, this is, we've got CH2, CH2OH. We have 3 propyl groups. CH2OH. We have 3 propyl groups. There's just 2. Oh, yeah, two propyl groups, yeah. Okay. Okay, so the longest chain here, no matter which way we go, is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, the alcohol takes priority, so this is pentanol. 1 pentanol. Okay, you have to have a 1, and it would be 2 propyl. 2 propyl, 1 pentanol. Okay, next we're going to look at compounds that contain more than 1 alcohol group. Okay, if you have 2 OH groups on the same compound, then it's a diol. If we have 3, then it's a triol, or it would be a tetraol, and so on. Okay, there's some text missing in this description. It says compounds containing 2 OH groups on adjacent carbons are called glycols. Okay. Okay, if they, we're going to talk later about something called a gemdiol, where we have 2 alcohols on the same carbon, but this is commonly called a glycol. Okay. So ethane is the carbon chain. Okay, notice we retain the E because the next letter is a consonant. So it's ethane diol, and we do need to locate those. So it's 1,2-ethane diol. This is the location of the alcohol groups. This is commonly called ethylene glycol. Okay, here we have 1,2-propane diol, or propylene glycol. This is 1,2,3-propane triol. This one is also called glycerol or glycerin. Okay, ethylene glycol and propylene glycol have both been used as automobile antifreeze. Ethane diol is very toxic. Okay, what does that matter? If antifreeze leaks out on the ground and animals such as dogs drink the water from puddles that contain antifreeze, they get poisoned. I'm not sure how many instances of that there are each year, but to treat ethylene glycol poisoning, the patient is given an IV of ethanol because receptors actually bind tighter to ethanol than they do ethylene glycol. Propylene glycol is also used in antifreeze. Its metabolites are much less toxic. Okay, 1,2,3 propane triol. This is a breakdown product of fats. Okay, fats are called triglycerides, and if you break down a fat, this is one of the products you get is glycerol. Glycerol is used as a moisturizer, a lubricant. It's also added to some foods because it absorbs moisture and keeps them from drying out. Okay, the reason that ethylene glycol and propylene glycol are good substances for use in antifreeze is they have three desirable properties. One is, of course, they have a high boiling point because you have two spots where hydrogen bonding can occur. So high boiling point. Water boils at 100 degrees Celsius. 1,2-ethane diol boils at about 189, so high boiling point. Ethylene glycol, propylene glycol are mixed with water in a car's radiator. Because of the OH groups, they're both very soluble, infinitely soluble in water. And it's actually a mixture of ethylene glycol and water, or propylene glycol and water, that's used as antifreeze and coolant. Okay, that mixture also has another desirable property, and that is a low freezing point, of course. Okay, these are good to about 40 degrees below 0 Celsius or Fahrenheit. Okay, in previous chapter, we looked at alkenes. Alkenes have priority over halogens and alkyl groups, but alcohols have priority over alkenes. Okay, so our longest chain here is 6, so that's hexane. Because of the double bond, we change it to hexene. So 3-hexene, this indicates the position of the double bond. And then this time we put the alcohol location right before the suffix. So 3-hexene, 1-ol. This is the location of the alcohol. Okay, and then the geometry is E or trans. Okay, let's look at the physical properties of alcohols. The COH bond in methanol is very polar. There's a partial positive charge on the carbon and the hydrogen. There's also a partial negative charge on the oxygen. So here's the electron paramagnetic map. The oxygen shows an electron-rich region. Okay, and then the other side represents an electron-poor region. The hydrogen on the oxygen, you can see this is a blue region. That is a partial positive region. Right, alcohols associate in the liquid state by hydrogen bonding. Okay, this is an especially strong attractive force between a partial positive on hydrogen and a partial negative charge on a nearby oxygen, or it could be a nitrogen or fluorine. And for alcohols, the strength of hydrogen bonding is about 2 to 5 kcal per mole. Okay, they're considerably weaker than covalent bonds. Okay, for example, the covalent bond for an OH is about 110 kcals per mole. But nevertheless, hydrogen bonding can have a significant effect on physical properties. Okay, this is a diagram showing hydrogen bonding of ethanol molecules in the liquid state. Okay, there's a strong attraction between the lone pair on this oxygen and this hydrogen on a nearby ethanol. Okay, the hydrogen bonds are shown with these dashed red lines. Okay, this is an example of a of intramolecular, that is within the same molecule, intramolecular hydrogen bonding. Okay, this is erythromycin A, an antibiotic. Okay, so the question here, how many hydroxyl groups are present? Okay, looks like there's one up at the top here. Actually two. We have one down here, one here, one here. Okay. The next question is how many amine groups? Okay. Let's see. Okay. Here's the amine group. This is a tertiary amine. Nitrogen's bonded to 3 carbons. Okay, and then the intramolecular or internal hydrogen bonding is shown. This hydrogen bond creates a 5-membered ring. Okay, are there any others? Okay, yeah, there's one here between nitrogen and OH. And then there's 3 more intramolecular hydrogen bonds. Okay, intramolecular hydrogen bonding is very important, for example, to the shape of certain proteins. Okay, most of us are familiar with the double helix of DNA. Okay, it holds its shape through intramolecular hydrogen bonding. Okay, so hydrogen bonding strongly affects 2 physical properties, namely boiling point and solubility in water. Okay, here we have a comparison of methanol and ethane. Okay, very similar molecular weight, but very different boiling points. Okay, 65 versus minus 89 degrees Celsius. Methanol is infinitely soluble in water, which means that you can never get a saturated solution. You can mix water and methanol in all proportions. Okay, ethanol is also infinitely soluble. And we can clearly see the effect of hydrogen bonding both on boiling point and solubility in water. 1-propanol is also infinitely soluble. 2-propanol is also infinitely soluble. It's not shown on the chart here. Okay, but as the size of the carbon chain gets larger, solubility goes down. Okay, so 1-butanol, okay, is no longer infinitely soluble, but instead it's about 8% soluble in water. And 1-pentanol, okay, the solubility drops even further, 2.3 grams per 100 grams of water. Screen. Try it again. Okay, so this is 1, 2, 3, 4, 5, 6, 7. Okay, so this is 1-heptanol. And although 1-heptanol would exhibit hydrogen bonding, the alcohol group represents a very small part of the overall structure. Okay, most of the properties are going to be dominated by this hydrophobic alkyl group, this nonpolar group. And so the most important physical property here will be the London dispersion. There's also going to be hydrogen bonding, but this would be much less soluble, in fact, almost insoluble in water. Okay, notice here that 1-butanol is only partially soluble in water. Okay, but when we have 2 OH groups, okay, such as 1,4-butanediol, that's now infinitely soluble in water. Okay, so adding extra OH groups increases the water solubility. Okay, so one more. Okay, as far as acidity of the OH hydrogen, alcohols are going to be pretty similar to water as far as their acidity. Okay, for example, the pKa, which is a measure of how strong the acid is, for water it's 15.7. For methanol, 15.5, so pretty close. We get this number, of course, by taking minus the log of the Ka. Ka is the conjugate base times hydronium over the undissociated acid. So methanol is about the same. Most alcohols are going to be a little bit less soluble in water, not soluble, acidic. Okay, here's a chart of some pKa values. HCl, of course, is a strong acid. It's put there just for comparison. Okay, its pKa is -7. Okay, each pKa unit is a power of 10. Acetic acid, okay, what we find in vinegar, 4.8. Most carboxylic acids are going to be about 4 or 5. Okay, alcohols will be about 16 to 18. Okay, so isopropyl is about 17, terphenyl is about 18 for its pKa. So these are weaker acids than water. Okay, the higher the pKa, the weaker the acid. Alcohols can behave as bases. Okay, in the earlier slide, something else was removing a hydrogen from the alcohol, and we got an alkoxide ion, in this case methoxide. Okay, just like water, the oxygen can get protonated. And this gives us an oxonium ion. Okay, we can't easily form the conjugate bases of alcohols with something like hydroxide because it's not a strong enough base. But one way that we can produce the conjugate base, this is actually not an acid-base reaction, but the result is the conjugate base of the alcohol, and that is to use an active metal, okay, lithium, sodium, or potassium. Okay, this is the pure element, so there's no charge. If we add sodium metal to methanol, okay, what happens is sodium gets oxidized. Okay, it loses an electron, and then hydrogen gets reduced. Okay, so here hydrogen had an oxidation number of +1. So each hydrogen gains an electron. In a pure element, the oxidation number is 0. Okay, so hydrogen gas is given off. Okay, the reason for doing this is these alkoxide salts are very useful in nucleophilic substitution reactions, for example, in making ethers. They could also be used as bases in beta elimination reactions. Okay, water-soluble tertiary alcohols can react very rapidly with HCl, HBr, and HI. This is actually a reaction that we do in lab. We start with tert-butyl alcohol, 2-methyl-2-propanol, react it with concentrated hydrochloric acid, and at room temperature, we get a substitution reaction. Okay, this is an SN1 reaction that takes place. Low molecular weight primary and secondary alcohols are unreactive under these conditions. Okay, last week in my lab, we reacted a primary alcohol with HBr, and we had to heat it to boiling for almost an hour in order to get it to react. Okay, so water-insoluble tertiary alcohols can react by bubbling HCl gas through the solution of the alcohol. And the alcohol is usually dissolved like in a solution of ethyl ether or THF. THF is a cyclic ether. All right, so this was actually a reaction that we did last week in my lab. We used 1-butanol and HBr to produce 1-bromobutane. Okay, this is how the mechanism takes place. Okay, OH is a poor leaving group, but in the presence of acid, oxygen picks up a proton, and now water is a much better leaving group. Okay, so water leaves, giving us a tertiary carbocation, and then in the last step, chloride attacks to form our product. Okay, there's a similar first step with primary alcohols, such as 1-butanol. The oxygen picks up a proton. We get the oxonium ion. Okay, but the carbocation is the primary carbocation would be too unstable. So instead, what happens is we have an SN2. So bromide has to come in and it hits this carbon number 1. So it forms a bond and then this CO bond breaks at the same time. And we get our 1-bromobutane with water as a leaving group. Okay, so reactions are governed by a combination of electronic and steric effects. Okay, this is a review of our previous chapter. Okay, tertiary alcohols are never going to react by SN2. Okay, they're too crowded for the nucleophile to come in. The primary alcohols will never react by SN1. And so SN2 is governed by steric factors, and SN1 is governed more by electronic factors, namely the stability of the carbocation. Okay, another way of converting alcohols to alkyl halides is to use this reagent called thionyl chloride, SOCl2. Okay, we can take an alcohol and react it with thionyl chloride. Okay, pyridine, let me draw the structure of pyridine. This is a solvent, and it also acts as a base. This is pyridine, and it's like benzene, except one of the carbons is replaced with a nitrogen. This is a good solvent. It dissolves a lot of organic compounds. And, okay, if we look at the balanced equation there, okay, we've got our alcohol reacting with thionyl chloride. Okay, this produces 1-chloroheptane. Okay, there's no rearrangement or elimination or anything like that. So we get 1-chloroheptane, and then we get SO2 and HCl as byproducts. Okay, those are both gases. And if you have byproducts that are gases, you can easily remove those. And so this reaction can go forward. Okay, we can easily prevent it from reversing, so we get high yields of product. Okay, remember back here, this first step is rapid and reversible. Okay, it takes a long time for this, an hour or so for this to reach equilibrium. Okay, this takes place fairly quickly. You get high yields. HCl reacts with the pyridine. And produces a salt. Okay, so this also helps remove the HCl, and that prevents the reaction from going backwards. Okay, another reaction that we can do with alcohols is dehydration. Okay, what this does is it removes an H and an OH from adjacent carbon. So this is a type of beta elimination. Primary alcohols must be heated at high temperatures in the presence of an acid catalyst such as sulfuric acid or phosphoric acid. Secondary alcohols can undergo dehydration at somewhat lower temperatures. Tertiary alcohols are easily dehydrated, and they can be dehydrated at only slightly above room temperature. Okay, the first reaction shown here, this is an important industrial process, conversion of ethanol to ethene or ethylene. Okay, and that takes place at 180 degrees Celsius. Cyclohexanol is a secondary alcohol. Okay, we can dehydrate it at 140 degrees, a somewhat lower temperature. And this is a reaction we commonly do in the laboratory, dehydration of cyclohexanol. Okay, so we're removing an H and an OH from adjacent carbons to get an alkene. Tert-butyl alcohol is very easily dehydrated. Notice the temperature about 50 degrees Celsius. Okay, so if you're, okay, let's go back to this reaction. Oops, this reaction right here. Okay, if you're doing the SN2, okay, notice the temperature here, 25 degrees or even a little bit below, because if you get it too warm, you're going to get an alkene. You'll get elimination as a byproduct. Okay. Just like with the E1 and E2 reactions of alkyl halides, okay, if we get more than one alkene product, the one that is most substituted generally predominates. This is what we call Zaitsev's rule. Okay, so if we dehydrate 2-butanol, okay, with 85% phosphoric acid, we get 2 alkenes, 2-butene and 1-butene. The internal alkene, the more substituted alkene, you can see is the dominant product. Okay, we get 80% yield is observed for that one. And 2-butene, we get a mixture of cis and trans. We get more of the trans, but 80% of both the 2-butenes. Okay, so this is how dehydration takes place. Okay, the first step is protonation of the oxygen with an acid. Okay, this is rapid and reversible. Okay, for a secondary or tertiary alcohol, we have water leaving. Okay, that's a slow step. And then in the third step, that water comes along and it removes a beta hydrogen. Okay, a hydrogen on the carbon next to the carbocation. Okay, that produces hydronium, and then the pair of electrons in the CH bond then moves to form the double bond. All right, so for a primary alcohol, okay, it starts out the same way. Oxygen gets protonated, but this is an E2 mechanism. It doesn't wait for water to leave. This requires a higher temperature. Water takes a beta hydrogen, kicks out water at the same time. Okay, in our chapter on alkenes, we saw that we can hydrate an alkene in the presence of a catalyst. This is just the reverse of dehydration. If we want to do a dehydration, we use a concentrated acid in a high temperature. If we want to do a hydration, okay, we want lots of water, okay, in order to shift it toward the alcohol. Okay, a strong acid like phosphoric or sulfuric is going to remove water. Okay, the next reaction is oxidation of alcohols. And the oxidation product that we get depends on whether we are starting with a primary, secondary, or tertiary alcohol. Okay, one way of oxidizing an alcohol is to use chromic acid. which we can form from chromium trioxide and sulfuric acid. Okay, oxidation in organic chemistry involves an increase in oxygen content or a decrease in hydrogen content, or both. Okay, so let me write that down. Oxidation. Increase in oxygen content. Decrease in hydrogen content, or both. All right, so going from this alcohol, 1-octanol, to octanal, which is an aldehyde, we are losing 2 hydrogens. Okay, one from the carbon, one from the oxygen. So that's an oxidation. Turns out that the aldehyde is so easily oxidized itself that it's not isolated. It goes all the way to the carboxylic acid. Okay, so this represents an increase in oxygen content. So we're adding an oxygen. Okay, the main message of this slide, okay, compared to this, is that if we use chromic acid and a primary alcohol, okay, we usually can't stop at the aldehyde. Okay, it goes all the way to the carboxylic acid. If we want it to stop at the aldehyde, there's a reagent that we could use called pyridinium chlorochromate, or PCC. This is the formula for PCC, and this is done in the absence of water. We use something like dichloromethane as our solvent. Okay, this allows us to stop at the aldehyde. Alkene groups can also be oxidized with many of these reagents, but notice here with PCC, the alkene groups are left intact. Okay, tertiary alcohols are not oxidized by either chromium trioxide, chromic acid, or PCC. Right, if we had a tertiary alcohol, okay, what is it going to be oxidized to? Okay, the problem here is we have 5 bonds. Okay. So that doesn't work. So there's no reaction with PCC or chromium trioxide. Okay, I'm going to go ahead and stop there. Okay, before we talk about ethers, I'll talk about some more of the commercially important alcohols, and then we'll talk about ethers and thiols next time. So I'm going to go ahead and stop the meeting.